Welcome everyone to the section 2.3, where we will talk about the first and the second derivative tests. So if you're surprised that the first video is the first derivative test, don't be. The second video, you probably know what that's going to be as well, even if you don't cheat on Canvas. The third video, though, that's a mystery, because there's no third derivative test, or at least not that we're talking about. I don't think it exists. So we're going to kind of relate what we talked about in the last couple sections with local extrema today. All right. So the idea is if we look at a local maximum or relative maximum, we use those words interchangeably. And if we look at a local minimum, then locally, what they look like is this. So the question is, what can we say about the first derivative? Well, something that we kind of know is that the first derivative at these critical points is 0, right? The slope of the tangent line at these local extrema is 0. And furthermore, notice that as we go left to right, the function is increasing, it's 0, and now the function's decreasing. For a local minimum, right, the function is decreasing, and then the function is flat, infinitesimally small area, and then the function's increasing. And this is essentially what the first derivative test is going to be, is that if the first derivative of a function equals 0, then we have a candidate for a relative minimum or relative maximum. And then we'll use the first derivative test. We'll look at the first derivative to see, well, is it going from increasing to decreasing? In which case, it's a local maximum. Or is the first derivative going from decreasing to increasing here? In case we'll have a local minimum. All right, so we're going to start off with the definition. If f prime at a equals 0 or is undefined, then the point a comma f of a, ooh, this might not fit, is, we'll fit it, a critical point. A lot of times that'll be abbreviated. Oh, the abbreviation doesn't fit. All right. The definition's good though. A lot of times that's abbreviated CP. All right. Because you know I love abbreviations. I hate writing things out the long way. All right. So specifically, that's what a critical point is. And what we're going to look at when we introduce the first derivative test is just relating this fact up here to what we've got. All right. So first derivative test says if we have a critical point, if a comma f of a is a critical point or CP, then if f prime goes from positive to negative, remember that's like going up and then going down. Going up and then going down, that's the top of a hill. That's a local maximum. All right? And this critical point is a local maximum or relative maximum. The second part of the second, ooh, getting a little ahead of myself. The second part of the first derivative test is very similar, right? And so what I'm going to do right here is just use some squiggles. Say, yes, if f prime goes from negative to positive, then this critical point is a local minimum. All right, so the squiggles just mean what we've written above, we're writing again, but we're going to save ourselves a little writing. Okay? So we can just look at how the sign changes to find local extrema as long as the point has either a derivative that equals 0, so it goes flat, or the derivative is undefined. We'll want to look at that case too. Let's kind of look at this with an example. All right. Example 1. Find and classify local or relative extrema for the function f of x. That's not an x, Jason. Nice try. There you go. Nice work, buddy. F of x is equal to 1/3 x cubed minus 2x plus 3x plus 1. All right. So we're going to find critical points. And then we're going to test them. We're going to look at the sign of f prime on either side. And that's how we're going to be solving these problems today. Okay? We'll show an example here with the first derivative. In the next video, we'll show an example for the second derivative. You can always kind of use either one with a small caveat for the second derivative test. But first derivative test will always work. So we're going to start. To find the critical points. Well, what was a critical point? I don't remember, Jason. We got a definition right here. The critical point is just where the derivative equals 0 or is undefined. We have to start by finding when the derivative equals 0, which means we have to start by finding the derivative. So the derivative here, we'll use the power rule. So that 3 comes down, right, when we take the derivative. 3 times 1/3 is going to cancel each other out. Subtract 1 from the exponent, we're going to get x squared. The derivative of 2x is just 2. Hold on. That's true, but there should be a 2x squared up here. I wrote the problem down wrong. All right, so the derivative of 2x squared, let's use the power rule again to get 4x. The derivative of 3x is 3. And the derivative of this last guy, derivative of a constant, is just 0. So this is our derivative function, and we want to know when is this derivative function equal to 0 or undefined. That's where our critical point is going to be. We just set it equal 0. You want to know when something's equal to 0, you just do that. Okay? Let's write that down on the next page. X squared minus 4x plus 3. Oh, that's not a minus sign. Minus 4x plus 3. When does that equal 0? Solve this equation. This is a quadratic equation. You can factor it. You can use a quadratic formula. You can complete the square. Feel free to reach out to me if you want some review. I got some videos on that stuff. All right. So we're going to factor here. This is a trinomial with a leading coefficient of 1. We need two numbers that multiply to positive 3, that add to negative 4. We're going to choose negative 3 and negative 1. So this is true when x minus 3 equals 0 and when x minus 1 equals 0. Solve both of these. We'll get two candidates for x coordinates of 3 and positive 1. Now, these are not our critical points, right? We wanted to find the critical points, and my claim is we have not found critical points yet. We found when they equal 0, but critical points, if the name will clue you in, are points. So we need x values and y values. So the critical points are going to be the x value is 3 with some y value, and the x value of 1, again with some y value, and we need these y values. Okay. Oh dear, what are you doing down there, little blue line? Oh, we need the y values. But luckily, we've got a nice function that takes in x values and spits out y values. We're going to try to find that real quick. So plug into the original function, not the derivative. Plugging into the derivative gives the slope of the original function. We want the y values of the original function. Off to the side, we'll plug in 3 into our original equation, which is going to be 1/3 times 3 cubed minus 2 times 3 plus 3 times 3 plus 1. We'll also plug in positive 1. All right. If you type this all out on a calculator, you should get 9 minus 6 is 3. 3 plus 9 is 12. 13 maybe? Well, now I'm getting nervous. Kind of a weird number. 9 minus 6. Oh, yep. This is 3 squared. I wrote it down wrong over here. All right, so it's not 13. Aha. My nerves. We're doing the right thing. So it's 9 minus 18, which is negative 9, plus 9, which is 0, plus 1 is 1. We do the same thing we're going to plug in 1 into our equation. Again, you could do that the same thing. We're going to get 1/3 minus 2 is negative 5/3 plus 3. We're going to get 1/3 minus 2 plus 3 is 1 1/3. Plus 1 is 2 1/3. I think it's 7/3. You use a calculator though, don't trust my math. All right, so we get the points 3, 1, and 1, 7/3, maybe. There might be a math error in here. All right. You know what, now, all right, I'm just gonna check my answer. All right, so we have 1/3 times 1 minus 2 plus 3 plus 1 is 2 1/3, which is 7/3. Excellent, great. So these are our critical points. Step 1, back here, has been completed. Next, we have our critical points. We need to look at the sign of the derivative on either side of these points. So this is what we're going to do. We're going to plug in these x-coordinates and see what happens on either side. Okay, so our derivative, remember, whoops, that's a big prime. Too big of a prime. Prime of x, we said, was x squared minus 4x plus 3, I believe. So we want to look at what's going on with the sign of f prime. So we're going to make a little chart. The x-coordinates of our critical points are 1 and 3. These are the x-coordinates. And I want to know what happens on either side in each of these intervals. What happens with the derivative in this interval? What happens with the derivative in this interval? And what happens with the derivative in this interval? We're going to comment on that. We're going to write, what is the sign of f prime in these intervals? Because we know that f prime equals 0 at these specific points. So what happens on either side? We'll just pick some points. So pick a point to the left of 1, maybe 0. Pick a point in the middle, maybe 2. Pick a point to the right, maybe 4. And we're going to look at the sign of the derivative here. If you plug in 0 into the derivative function, you should get 3. So over here, the derivative is positive. It's going up. Let's use another color for this because I love colors. Positive, which means to the left of this point, to the left of this critical point, we're increasing. Remember, a positive derivative means the function is increasing. You plug in 2 into our derivative function, you should get 4 minus 8 is negative 4, plus 3 is negative 1. So now in this interval, we have a negative derivative, which means the function is decreasing. So right off the bat, we know something about this critical point, because at this critical point, the function's going from increasing to decreasing. And that was our first derivative test. If the derivative goes from positive to negative, so if the function goes from increasing to decreasing, this critical point's a local max. Great. Let's keep on going. If we plug in 4 into the derivative function, we get 16 minus 16 plus 3, which is 3. That is a positive number last I checked. The function is again increasing. So right over here, we go from increasing to decreasing, local max. Over here, we go from decreasing to increasing, local min. So we conclude our answers by saying the point 1, 7/3 is a local max. Right? And you can kind of see it over here, right? Like there's a little hill in our drawing. The top of a hill is local max. And the other point, which I believe was 3, 1, is a local min. And again, because it's going from decreasing to increasing. It's like the bottom of a valley. And that's the first derivative test. All right, there are some other examples of the applications of first derivative tests in the textbook, so feel free to check those out if you want. And if you have any questions about this or are a little unsure about what we're doing with this chart, go ahead and ask me that as well. All right, but otherwise, I'll see you in the next video. You'll see me in the next video. I won't see you at all unless you come to office hours or something like that. Good luck.